The cosmos, a boundless tapestry of stars and voids, beckons us with its eternal mysteries. Within its vastness lies the enigma of the origins of life and the nature of consciousness itself. Each celestial body, a silent witness to the universe's secrets, sparks questions that transcend our understanding. In the depths of space, we confront the profound interplay of creation and destruction, order and chaos. As we explore the infinite, we embark on a journey not just through the cosmos, but through the very essence of existence and our quest to uncover its hidden truths. From the mysteries of what caused cosmic inflation just after the Big Bang, to questions disrupting our perception and understanding of time, all the way down to the imbalance between matter and antimatter. The cosmos is filled with many such mysteries, both scientific and philosophical. A city of rich cultural heritage and intellectual fervor was the fertile ground where a curious and scientific spirit first took root. In the heart of Vienna, young Erwin Schrödinger's childhood was steeped in wonder and spirit of inquiry, nurtured by his father's scientific pursuits and a home filled with books. This early immersion in the mysteries of the natural world planted the seeds for his later work in quantum mechanics. Throughout his life, Schrödinger's quest for understanding transcended the boundaries of science. As he delved into the philosophical depths of existence and the nature of reality. In 1935, he posed a thought experiment to Albert Einstein, challenging the established theory that precise quantum calculations will yield precise outcomes. It is known as Schrödinger's cat experiment. This became one of the great paradoxes of science, a mystery of quantum mechanics, where an observer's decision affects the outcome. This experiment holds significant relevance in understanding the mysteries of the cosmos by highlighting key aspects of quantum mechanics that have profound implications for the nature of reality and the universe. The cosmos hides many mysteries, some more daunting than others, with others more commonplace than some. Hence forces us to ask ourselves, how did the universe begin? And what was the cause of the Big Bang? What are the largest structures in the universe? And how did they form? And more importantly, to know and understand what mysteries lie in the uncharted regions of the universe. You are watching Space 9, unveiling the mysteries of the cosmos, your gateway to the universe. The nature of continuum. It is still a poorly understood dimension, with questions about why it flows in one direction and how it relates to space and gravity in the context of general relativity and quantum mechanics. We widely know this as time. Time is a universal concept and probably the most important concept used for measuring the evolution of everything in existence. To us, time is linear. We remember the past, we experience the present, and we anticipate the future. With time, we move from one moment to the next. We feel this in the changing of the seasons, from winter to spring, and we feel it in the rhythms of dance and song. We see it as age, seeing our kids grow older with each passing year. Time is a fundamental part of the human experience. But over the centuries, scientists and philosophers alike have questioned the perceived linear nature of time. They've questioned if time is really as one-dimensional as we perceive it to be. They're divided as to whether time, or at least our perception of it, is real or just an illusion. Is time truly linear? Or is the fact that we live one moment at a time only an illusion? What if the past, present, and future are all existing at once? Let's take a look at it. We might think that time flows in one direction, from past to present to future. But here's a fun fact. The laws of physics don't demand that time only move forward. The laws of the universe work just as well, whether time is moving forward or backward. Some theories state that as the universe gets older, it'll begin to contract, with all the gravity from all the stars and galaxies pulling the universe in on itself. Well, as this happens, time might start to run backward until the universe gets hotter and denser, till it reaches a critical point, just like a Big Bang, but in reverse. This unlikely possibility of time moving forward as well as backward challenges our linear perception of time. This has led some scientists to believe that time is simply a human construct, and that we exist in a block universe where time and space are interconnected. In this theory, all events that have occurred are occurring, and will occur, have their own unique moment and coordinates in four-dimensional space-time. This means that the concepts of past, present, and future are human constructs. All events, both past and future, are simultaneously occurring at once in their coordinates in space-time. The day you took your first steps as a child is as real as what's happening in this present moment. The concept of a moment passing doesn't exist, as they aren't simply gone or erased, but are still existing in space-time. Max Tegmark, a renowned physicist at MIT, explained the time paradox in a rather simple way. He stated that we could view time in two ways. The first, as a three-dimensional space where things happen over time, the same way we already perceive time. Or as a four-dimensional space where nothing actually happens and everything just is, existing in their respective positions in a block reality. With the latter, time truly is an illusion, as nothing really changes. Everything that has ever happened, is happening, or will happen are all happening at once. It's a lot to think about, and maybe even difficult to comprehend, but isn't it fascinating? Simply being able to doubt what we think we know has been the foundation of groundbreaking discoveries, not just in science, but in every area of life. Consider our understanding of the solar system in the last 2,000 years. The first solar system model was the geocentric model, where scientists believed that Earth was the center of the solar system. This model was accepted for well over 1,000 years, until it was later disproved by Nicholas Copernicus. Copernicus presented the radical idea that Earth was only just another planet in the solar system, and that became the norm. Then came Isaac Newton a few centuries later with a fresh understanding of gravity. He revealed that every body of mass in the universe exerts its own gravitational pull on other bodies. He popularized the understanding of the Earth's rotation around the Sun and the Moon's rotation around the Earth. Then came Einstein's theory of general relativity, which redefined our understanding of gravity. Einstein's theory of massive stellar bodies causing a curvature in space-time has been the guiding theory for most of the 21st century. The transition from a geocentric model of the solar system all the way down to Einstein's theory of relativity shows how questioning accepted theories can push the boundaries of our understanding. Even now, despite the solid foothold of Einstein's theory of relativity, scientists continue to question, investigate, and push the limits of accepted science. The theory of our understanding of time is supported by Einstein's theory of relativity, but it is challenged when it comes face to face with quantum physics. Quantum mechanics completely shatters the theory of relativity in more ways than one. For instance, quantum particles can exist in two places at once. Communication between quantum entangled particles is instantaneous, even across millions of light years. Erwin Schrödinger's experiment has proved that quantum communication is the only thing in the universe that can travel faster than the speed of light, a limit that Einstein's theory of relativity says is impossible to surpass. So, the limits and our perceived perception of what time is and how it moves could soon be upended, and a new understanding of the realities of space-time could soon be reached. But until then, we're left to ponder on if time is real or simply just an illusion. Baryon asymmetry. Another biggest mystery in modern astronomy is the imbalance between baryons, which are protons and neutrons, and their antiparticles, also called antibaryons. There is also the asymmetry and mystery surrounding it. The bad phenomena, and the most famous one, would be antimatter. So why is antimatter such a big deal in the world of science? Well, it is like a mirror reflection of matter, but with opposite properties. It's composed of antiparticles that have the same mass as particles of ordinary matter, but opposite charge and characteristics. For instance, an electron in regular matter has a negative charge, but its antimatter counterpart, the positron, carries a positive charge. Understanding antimatter is key to comprehending the origin and evolution of the universe. When matter and antimatter come into contact, they annihilate each other, releasing a tremendous amount of energy. This annihilation is a fundamental process that has significant implications for astrophysics and cosmology. The existence of antimatter also raises one of the biggest mysteries in physics. Why is there more matter than antimatter in the universe? This imbalance is crucial because without it, the universe as we know it, with galaxies, stars, planets, and life, would not exist. At the beginning of the universe, just after the Big Bang, it's believed that equal amounts of matter and antimatter were created. However, matter dominated for reasons not yet fully understood. It is still the biggest mystery. Hence, this asymmetry is a central puzzle in modern physics and is crucial for explaining the universe's very existence and everything in it. Thankfully, there isn't much antimatter in the universe, else there would be nothing left to observe. Unlike dark matter, scientists have actual proof that antimatter exists, and they can actually be created in labs for experimental purposes. The major problem with antimatter lies in its abundance or lack thereof in the universe. The observable universe is predominantly composed of matter rather than antimatter, but the reason for this imbalance remains a major question in physics. It is noted that the Big Bang was a perfect cosmic soup with just the right amount of heat and energy, resulting in the beauty that is the cosmos we see today. If that was the case, the Big Bang should have created equal amounts of matter and antimatter. But from our observation of the universe, that's far from the case. Everything we see today, from the largest stars to the smaller life forms on Earth, are entirely made of matter. On the other hand, there is not much antimatter to be found in the universe. The universe is made up of about 5% ordinary matter and less than 0.0004% antimatter. That's a huge disparity in quantity between particles that ought to be mirror images of each other. For a universe that's almost perfect and believed to have created equal numbers of particles and antiparticles, this disparity has puzzled scientists for decades. Something must have occurred at some point since the Big Bang to have tipped the balance in favor of matter. This mystery is particularly daunting as the Big Bang is believed to have had a balanced equation to have successfully resulted in a universe like this. As such, any imbalances in energy, heat, particle size, charge, or quantity should have nullified the entire equation, and the universe would have not come into existence. Scientists now assume that although the initial parts of the Big Bang were perfectly symmetrical in all aspects, there was a period of cooling and some unknown physical or chemical process tipped the scales in favor of baryons. This is known as baryogenesis, the phenomenon in which the universe evolved to contain more baryons or matter over antibaryons or antimatter. However, this excess of baryons over antibaryons shows that this imbalance contradicts some laws of physics, and physicists are eager to find out why. Where have all the antiparticles gone? To answer this, Russian physicist and Nobel laureate Andrei Sakharov came up with 3 fundamental conditions that help break down the puzzle that is baryogenesis. The first condition is the baryon number violation, which states that there must be factors capable of violating a standard symmetrical system, which then ultimately leads to an imbalance of matter over antimatter. The second condition is known as CP violation. This condition simply states that the laws of physics are not the same for particles and their corresponding antiparticles. This would allow for a system to have an imbalance of baryons to antibaryons under specific circumstances. The third condition is known as thermal non-equilibrium. This condition postulates that the universe must have had a period of thermal non-equilibrium. This state would have allowed for baryon-antibaryon asymmetry, which favored the abundance of baryons over antibaryons. These conditions have to have been present at some point during the early universe to have enabled the imbalance we see in the baryonic system today. Either 1, 2, or all 3 must have come into play at some level or in some mysterious combination, the result of which we now observe in the universe. One pressing question that has challenged the conditions put forth by Andrei Sakharov is that these conditions weren't present, and the universe just simply came into a state of baryonic imbalance all on its own. While that may be an entirely possible scenario, we have to consider that everything in the universe is a result of cause and effect. Nothing simply just happens. All we see and observe are results of a combination of pre-existing factors. Factors that, when replicated, would produce the same result we see. Take a coin, for instance. If you spin said coin on a table, it has only 2 end results, either landing on heads or tails. But it cannot be said to be either until it stops spinning and lands on either side. The coin has a 50-50 chance of landing on heads or tails. In essence, if multiple coins are spun in the exact same way, logically, half of them should land on heads and the other half on tails. Following this same logic, half of the particles present in the early universe should have decayed into equal parts of matter and antimatter. However, if a stone is rolled across the table of spinning coins, such that any coin it hits lands on heads, this would disrupt the whole system. There would now be more heads than tails, since an external force is now at play in the system. In the same way, the Sakharov conditions could have been the added interference to a previously stable system of oscillating particles, causing more to decay as matter as opposed to antimatter. Physicists try to study what these processes might have been by studying the differences in the behavior between matter and antimatter. The one place such study can take place is at the Large Hadron Collider at CERN. Here, high-energy proton collisions are created, and the resulting interactions are studied to better understand how the universe works on a subatomic level. As such, finding out the true nature and mechanisms behind dark matter, dark energy, and baryogenesis remains one of the most daunting problems of modern physics. And although the solution to each problem might not be related, it is, however, not far-fetched to assume that at subatomic levels, some unifying new physics might present a solution that solves most, if not all. There are other matters which are considered dark in nature. Like normal matter, Dark matter has mass and occupies space, but unlike normal matter, it doesn't absorb, reflect, or radiate light. Dark matter is completely invisible to us as it emits no energy or light that we can detect. So the big question is, how can we know it exists if we can't see or even detect it? The answer is gravity. Gravity is the force that acts on any object with mass. With the fundamental principles of mass and gravity, scientists are able to calculate the mass of stellar objects light years away. Basically, we can tell the mass of an object by how fast it spins due to gravitational pull acting on it by the star or galaxy closest to it. Swiss astronomer Fritz Zwicky studied the movement of spiral galaxies in the Coma galaxy cluster, which contains over 1,000 galaxies. He observed that these galaxies contain more stellar bodies closer to the center and less as you approach the outer edges. Ideally, the laws of physics dictate that the densely packed center of these galaxies should be spinning much faster than the outer edges, as they have more mass. But somehow, the stars in both the center and the outer edge of these galaxies moved at the same velocity. This indicates that there must be more mass in these galaxies, which appears to be balancing out the gravity exerted. This extra mass could not be seen, but definitely exerted a powerful gravitational effect, and hence the term dark matter was coined. A type of matter that cannot be seen, but is most definitely present. As we all know that scientists calculated the gravitational effects of dark matter in the universe is over 27% of the known universe. Normal matter only accounts for about 5% of the universe, meaning dark matter is more abundant in the cosmos on a grand scale. According to the theory of general relativity, dark matter explains the behavior of sound waves and radiation that was abundant at a time when the universe was less than 400,000 years old, which we are able to see as CMB radiation. Theories of modified gravity fail to account for these lapses of mass and gravity across the board. Another important question you might be wondering is, where does dark matter come from? Well, there are a few theories explaining the origins of dark matter. One of them being that they originate from black holes. A paper published in the Astrophysical Journal in December 2021 states that black holes are prime candidates for producing dark matter. For one, we can't observe beyond the event horizon of a black hole because we can't detect light beyond it, which is consistent with the invisible nature of dark matter. Also, the incredibly dense nature of whatever invisible matter contained in black holes holds well with the incredible mass of dark matter in the universe. So many possibilities, and yet so little evidence to back them up. There is something even more elusive: dark energy. Dark energy is a force that is exerting a negative pressure on the universe, stretching the very fabric of space and time. Think of dark energy as an anti-gravitational force, or the evil twin of gravity. While gravity holds cosmic objects together, dark energy pushes them apart and is doing so at an increasing rate. Although dark energy is more abundant in the universe, scientists know even less about it than they do about dark matter. So how do they know it exists if they don't know much about it? Well, since the early 1900s, astronomers have hypothesized that the universe is expanding, but they weren't sure. For some reason, the known expansive forces traced back to the Big Bang aren't all that's stretching the fabric of space-time. There appears to be an extra force with a repulsive gravitational effect speeding up the expansion of the universe. This force is dark energy. One of the major questions posed by the existence of dark energy is, how do we know the expansion of the universe caused by dark energy isn't just traced to the Big Bang? Well, the known cosmological model of the universe concludes that there should be a relatively steady stretch and expansion of the universe as a result of the Big Bang. The explosive cosmological wave that gave rise to our universe is forever infinite and should have been relatively constant since it began some 13.8 billion years ago. However, our studies of exploding stars revealed that around 5 billion years ago, the rate of expansion sped up and has been increasing since that time. This leads us to conclude that a different factor aside from the Big Bang is responsible for this increase in the expansion of the universe. This different force is dark energy. You might be thinking, since dark energy is so powerful and is expanding the fabric of space itself, why aren't galaxies getting scattered as space stretches? Well, this is where dark matter comes in. As dark energy serves to expand space on a large scale, dark matter holds regions of mass-like galaxies together, keeping them from stretching and spinning out of control. In essence, dark matter and dark energy could be seen as having opposite effects on the universe, balancing each other out. However, dark energy will prevail, as it will eventually rip galaxies so far from each other that we won't be able to detect their light no matter how advanced our telescopes become. The Big Bang and cosmic inflation. Science today has a generally accepted picture of what the early stages of the universe looked like. This is something we've all come to study, understand, and accept as the Big Bang Theory. The theory basically states that about 13.8 billion years ago, our universe was smaller, hotter, and denser than it is today. The universe emanated from a portion so small that there are no measurements in physics that could calculate just how dense and hot the nature of this early universe was. In this primordial minuscule universe, all particles and elements that make up the universe we see today were spurned into creation in less than a second. The very events that led to or caused the Big Bang remain the biggest mystery in modern astronomy. All we see and observe, from the stars to galaxies, and even our very own little blue planet, all resulted from a space smaller than an atom. The temperature of the universe at the time of the Big Bang was a trillion times hotter than all the stars in the universe combined. Scientists have been able to study the leftover electromagnetic radiation from the young universe, known as the cosmic microwave background, or CMB. With information from studying how light and energy are spread out in the CMB, we've been able to measure how the abundance of light and elements line up from near the very earliest moments of the Big Bang. It's been widely accepted that the Big Bang originated from a single point known by scientists as the singularity. This singularity itself didn't already exist in space, but rather it caused the creation and expansion of space-time itself. In simple words, the singularity that caused the Big Bang existed in nothing, but created everything. The singularity had the precise amount of heat and energy needed to balance the creation and existence of everything we see and observe in the universe today. In essence, if the singularity was just a little bit hotter or colder at any point during the Big Bang, the universe we see today wouldn't have existed. However, the singularity was the perfect soup of heat and energy that created a near-perfect universe capable of sustaining life. This is simply mind-boggling to comprehend, but it further begs the question: what could have created such a perfect combination of energy and heat that resulted in the universe? Although we've made some progress in understanding the processes that took place during the Big Bang itself, one pressing question still remains unanswered. Since the Big Bang created all there is and all there was, what caused the Big Bang itself? One of the constant laws of physics and quantum mechanics is that energy can neither be created nor destroyed, and matter begets matter. For something to exist, there must have been something, or a combination of pre-existing components for something to be created. So, how is it that something as complex and powerful as the Big Bang resulted from nothing? Well, there are a number of theories that attempt to answer this universal question, and they all have different angles with which they tackle the conundrum that is creation. Although the theories differ in their approach to solving the creation problem, one common conclusion that they all share is that some pre-existing factor or entity must have caused the Big Bang. Some theories have gone as far as suggesting the presence of some supernatural or divine being that must have existed outside of space-time to cause the creation of the universe. And while that theory is ambiguous enough that it perfectly fits the holes in the creation problem, there are more scientific theories that attempt to tackle this mystery. There's the theory of the Big Crunch. This theory postulates that as a result of the expansion of the universe, the cosmos will eventually expand to a limit where the gravitational pull of matter across the universe will eventually slow the rate of expansion. The rate of expansion will slow so much that gravity will eventually begin to pull all matter in the universe together. The Big Crunch theory believes that in some distant future, the force of gravity exerted by every body of mass will eventually cause the universe to contract. This cosmic force of attraction will lead to the universe contracting, causing the ultimate collapse of the universe. The Big Crunch is essentially a reverse of the Big Bang, of which the end result will be a universe so compact, dense, and hot that it violently explodes, creating a whole new universe. Supporters of the Big Crunch theory believe that the death of one universe leads to the birth of another. In this theory, our universe didn't come from nothing, but actually resulted from the collapse of a pre-existing universe. But this leaves open another question. If our universe is a result of a pre-existing universe, then that universe must have been created from a long line of pre-existing universes. So herein lies the problem. If there has been an immeasurable line of universes, how did the very first universe come into being? And with this, we're back at square one. The mystery that is the creation of the universe. There's also the theory of the multiverse, where an infinite number of parallel universes exist without ever coming into contact with each other. These universes are believed to have different laws of physics guiding them, or may even have similar components, but in different shapes and forms. But even this theory fails to answer how each universe originates and what preceded them. While science keeps searching for answers to these questions, philosophy and faith believe in the existence of a creator, a cosmic being existing outside of space-time. This may subscribe to sentiments outside of science, but even renowned scientists like Neil deGrasse Tyson and others have entertained the possibility of a godlike being. What do you think? While we ponder on the origins of the universe, there is another mystery associated with the Big Bang, and that's the mystery of inflation. Cosmic inflation was a period of exponential expansion and growth spurt of the universe just after the Big Bang. The very instant of the Big Bang itself is the biggest mystery of all, but following that is inflation. Scientists believe there was an inflationary period that caused an unusual expansion of the universe. But the mystery lies in what caused it and the sheer, unimaginable scale at which it happened. The mystery of cosmic inflation is a huge problem in conventional science because it directly contradicts the general consensus of gravity being the only driving force after the Big Bang. Let's look at it. The observable universe is insanely huge, and we say observable because regardless of how large the universe seems, 93 billion light years across to be precise, it is still just the edge of all we can see. It's so huge that objects at the edge should never have been in contact, because not even light is fast enough to catch up with the expanding universe. But the universe wasn't always this large. So at some point during the early universe, these points would have been close enough that communication would have been possible. The inflation period did a lot more than just expand the universe. It caused the apparent flatness of the universe as well. The cosmic microwave background allows us to calculate the effects of cosmic inflation on the fabric of the universe, and the answers we get are quite strange. Let's consider a flat piece of paper. If you draw a triangle on this paper, you get a shape which that if you add up the angles, the answer you get is always 180 degrees. This is true for any flat surface. All the sides of a triangle add up to 180 degrees. But if you draw the same triangle on a curved surface, like say on a ball, the angles add up to more than 180 degrees. The same applies if you draw a triangle on an inverted surface, like on a saddle or the inside of a bowl. The angles add up to less than 180 degrees. With this, scientists have been able to calculate the curvature of space and determined that it is nearly entirely flat, save a fraction of a percent. In essence, the universe is ever so slightly curved, 0.04% actually. We won't bore you with the physics of it all, but what this means is that cosmic inflation caused the early universe to expand magnitudes faster than the speed of light. It increased the size of the universe by at least a factor of 10 to the power of 26. That's a trillion times its original size. And all this happened in a millionth of a second. The question is, what could be so powerful to expand the young universe to such magnitudes after the initial shock of the Big Bang? What's more shocking is that after inflation stopped, in the 13.8 billion years since the universe has managed to expand to the same extent that cosmic inflation achieved in a fraction of a second. This means that the gravitational waves that caused the universe to expand since the Big Bang are a trillion times weaker than the force that caused cosmic inflation. Scientists are still at a loss at what could have caused cosmic inflation. And we know what you must be thinking. Couldn't cosmic inflation have resulted from the force of the Big Bang? Well, seeing how the rate of cosmic inflation started and stopped within a fraction of a second, only for the universe to continue expanding in a more or less uniform manner since then, it is logical to conclude that some external force started and stopped inflation. What this force was and how it was able to do so much in so little time, and was even able to stop itself, is a complete mystery to science today. Neutrino mass. Neutrinos are nearly massless particles, but the exact mass and the reason for their extremely small mass compared to other particles are unknown. If you were asked what the biggest mysteries in the universe are, you'd probably list things like the Big Bang, dark matter, antimatter, and the rest of the theories we've discussed in today's video so far. But there's one fundamental mystery that links most, if not all of these, and that is neutrinos. More precisely, why do neutrinos have the mass that they do? Neutrinos are complicated little particles that are incredibly hard to detect and study. You might be thinking it's probably because they are very rare, but that's not the case. Actually, neutrinos are the second most abundant particles in the universe, second only to photons, which are particles of light. In reality, billions of neutrinos are passing through your body at this moment, but you'd be lucky to detect even one. That's because these particles don't interact with every other particle in the universe. And seeing as how we can only study and observe particles based on their interactions with other particles, you can see how hard it is to study neutrinos. This has earned them the nickname, the ghost particles. However mysterious neutrinos are, we've managed to solve a few mysteries about them. Firstly, we know that there are 3 types of neutrinos, and each of these is related to one of 3 other types of particles: muons, electrons, and tau particles. So we have muon neutrinos, electron neutrinos, and tau neutrinos. Secondly, we know that these neutrinos have mass. Now you might be wondering, well, that's obvious. All particles have mass. Well, it wasn't obvious with neutrinos. That's because detecting them is hard enough. It took almost 40 years after their discovery to conclude they had mass. Scientists were able to do this using a clever experiment. 2 teams studied neutrinos coming towards Earth from the Sun. What they expected to see was a certain number of neutrinos coming from our host star, based on what they knew about these ghost particles at the time. But what they observed was that the neutrinos that reached Earth were only about 30% of what they expected. After a series of follow-up tests, they discovered that the other 70% did in fact reach Earth, but they had suddenly turned into the other 2 types of neutrinos, tau and muon neutrinos. This discovery was surprising to say the least, so surprising that it won the team a Nobel Prize in physics. This is because the laws of physics state that changes like that are only possible when particles have different masses. This implied that for these particles to have different masses, they had to have masses in the first place. But that unlocked another mystery about these ghost particles: how to calculate the masses of neutrinos. This is extremely complicated and involves some rather complex quantum physics. The basics of it is that any type of neutrino can come in one of 3 different masses. So if, for instance, we detect an electron neutrino, there is a possibility it will have either mass number 1, 2, or 3. But there's more. The odds of measuring one of the 3 different masses are different for each type of neutrino. The probability of an electron neutrino having mass 1 may be 80%, but a tau neutrino would probably have a 20% chance of having the same mass. But as though that wasn't mind-boggling enough, scientists have no idea what these masses actually are. Neutrinos are so light and hard to observe that we've been unable to measure what their masses actually are. You might be wondering, why is any of this important, and why do we need to study tiny particles like this when we have real issues, like what happened during the Big Bang, to worry about? Well, the universe is made up of tiny building blocks, which are particles at the most basic level. So in order to understand events like the Big Bang, we need to understand how the universe works at its most fundamental level. This makes studying things like neutrinos all that more important. We get to understand how and why the universe moved the way it did, and maybe even predict how it will all end. The universe is filled with more questions than answers, and even with our present knowledge, we still don't know up to half of what we ought to. There are more mysteries to solve, and it seems the more we solve, the more mysteries we uncover. But that's the beauty of the universe. It's an endless sea of possibilities, giving us a broad canvas on which to build whatever our minds can conjure up. So don't stop asking questions. Don't stop questioning what is widely accepted. Let us know which mystery interests you the most. Thanks for watching.